We're starting in a few minutes. All right, welcome. Let me just set up my environment. We need to open up a terminal. CD2 projects. Rust. And then I need to open up Rust programming language. Learn Rust. Read the book. Yesterday we stopped at understanding ownership. Yeah, so maybe we just go through once again just to refresh our memory, because this is one of the most important concepts, I think, in Rust. So ownership. Ownership is a set of rules that govern how a Rust program manages memory. And then we have the stack and the heap. Stack and heap. Let's see what are the important points here. Both stack and heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. So that is stack. What are the key points as well for stack? All data stored on the stack must have a known fixed size. Data with an unknown size at compile time or size that might change must be stored on the heap instead. So anything that has fixed size at compile time goes into the stack, while the heap, what goes into the heap is a size that might change. Okay, so the heap is less organized. You have to request a certain amount of space. The memory allocator finds an empty spot. The heap that is big enough marks it as being in use and returns a pointer, which is the address of that location. This process is called allocating on the heap and sometimes abbreviated as just allocating. I think there was a nice analogy here we've read yesterday. It was about, this one. Consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A and then order from table B, then one from table A again, and then one from B again would be much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as it is on the stack rather than farther away, as it can be on the heap. Keeping track of what parts of code are using what data at heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Ownership. Once you understand ownership, you won't need to think about the stack and heap very often. But knowing the main purpose of ownership is to manage heap data and data can help explain why it works the way it does. Okay. Ownership rules. Each value in Rust has an owner. There can only be one owner at a time, and the owner goes out of scope, the value will be dropped. Okay. Variable scope. Okay, this is the first example. A scope is the range within the program for which the item is valid. Let s equals hello. Okay, so hello is a string literal, and usually these curly brackets would define the scope. S is valid from this point forward. You can do anything with S. Then after this closing curly brace, this scope is now over and S is no longer valid. In other words, there are two important points in time here. When S comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Okay. String type. To illustrate the rules of ownership, we need a data type that is more complex. So string is a bit more complex. Maybe we can jump somewhere here. So yesterday, this is string : which is an operator, allows us to name spaces particular from function. So from is a function. And then there's a string literal here, which is hello. Okay, and then, okay, this one demonstrates that S can be mutable. And in this command, S push str, okay, hello, and then this one will append. It says append, so it's like you're concatenating the string. So if we run this, it will show hello world. So what's the difference here? Why can string be mutated but literals cannot? The difference is in how these two types deal with memory. Okay. Memory allocation talks about the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we're done using the string. So from its implementation requests the memory it needs. Okay, second part is different. So there's this garbage collector in languages. In languages with garbage collector, the garbage collector keeps track of and cleans up memory that isn't being used anymore. Okay, so we don't need to think about it. It's our responsibility to identify when memory is no longer being used and call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. So in Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example using a string instead of string literal. Okay. So this is a string. When S goes out of scope and the variable goes out of scope, Rust calls a special function for S. The function is called drop. And it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly brackets. So closing curly brackets, then the drop will be called. Okay, so mention C++ here also. So in C++, there's a pattern, RAII. Resource acquisition is initialization. Yeah, but this is done by Rust automatically. That's what I understood from what was explained here. Okay, moving on to variables and data interacting with move. Okay, so another concept. Move. Multiple variables can interact with the same data. So we look at this example. So we have 5, and then x, and then x is assigned to y, or x and bind it to y. We now have two variables, x and y, both equal to 5. This is indeed what's happening because integers are simple values with non-fixed size. Okay, integers, fixed size, it means it goes into the stack. And these two 5 values are pushed onto the stack. Okay, however, for string, this looks very similar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2. But this isn't quite what happens. Okay, so in this figure, string is made up of 3 parts. We have, okay, I think it's referring to this, pointer, len, and capacity. This group of data is stored on the stack. This one is on the stack. On the right is the memory on the heap that holds the contents. Okay. The length of how much memory in bytes the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. So when we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on stack. So it means that in this statement, first S1 we have this, hello is over here in the heap, I mean somewhere in the heap, and then when this statement is evaluated, it creates something like this. So it does a copy, but it's only copying these 3 things, pointer, len, and capacity. So both are pointing to this location in the heap. Okay, it says here the representation does not look like figure 4-3. So it's not this. It's why? Because if Rust did this, the operation s equal to 2 could be very expensive in terms of runtime performance if the data on the heap were large. So try to imagine hello is not just hello, it could be grandmother's story. So by just copying S1 and S2, then you'll be consuming the heap and you would have nothing left. So it's very expensive. Earlier we said that when a variable goes out of scope, Rust automatically calls a drop function. But figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as double free error, and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, the line let S2 equals to S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. Okay, so this one will have an error. S1 is used here, but Rust considers S1 as no longer valid. So does it mean that it frees up it frees up S1. Okay. And according to this error, move occurs because S1 has type string, which does not implement the copy trait. So there's another concept, copy. Value borrowed here after move. Note this error originates from macro. Okay. Then it suggests clone. Yeah, but maybe we'll see how to properly fix that issue. If you have heard the term shallow copy and deep copy, so now we have ownership, move, and then what else is here? Ownership, move, shallow copy, and deep copy while working with other languages. Okay, so this is from other languages. The concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. Shallow because you're not copying the data itself. It's only the pointer. It's known as a move. Okay, so let's try to understand this. So if you have let S2 equals S1, so it is actually doing a move like this, so meaning S1 is no longer valid. Now it has the same pointer length and capacity value, which points to hello. That solves a problem with only S2 valid. When it goes out of scope, it alone will free the memory, and we're done. In addition, there's a design choice. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. So this is good. Nothing would be inexpensive in terms of runtime performance. Okay, let's move on. Scope and assignment. The inverse of this is true for a relationship between scoping, ownership, and memory being freed by a drop function as well. When you assign a completely new value to an existing variable, Rust will call drop and free the original value's memory immediately. Okay. When you assign a completely new value to an existing variable, Rust will call drop and free the original value's memory immediately. So the previous one is freed immediately. Consider the code. String, but this is mutable. It means that S can change. Okay, so here's the diagram. So at this point, you have this. So S is mutable, this is mutable. And then hello, wait. Scroll down a little bit. I think it started with this. So this line did this, where you have the pointer pointing here. And then the second line, S, the value of S changed because it's mutable, and now it's creating this. So the pointer is pointing here. And then when you print S, it's going to be ahoy world. Yeah. Okay, we initially declare variable S, bind it to string, the value hello, and then we immediately create a new string, the value ahoy, okay, this line, and assign it to S. At this point, nothing is referring to the original value on the heap at all. So this one, it's grayed out. So what will happen? The original string thus immediately goes out of scope. Rust will run drop function on it, and its memory will be freed right away. When we print the value at the end, it will be ahoy world. Yeah, it will be ahoy world. Let's try something. What if S is not mutable? Let's check our understanding. Okay, so let me go to one of my folders the other day. Ownership. Okay. Let's open Visual Studio Code from here. Okay, so let's delete all of these. Using VI here. Okay. Let mat s is string colon from hello. And s was to set string colon from ahoy. Set ahoy. It's the error here. Cons. syntax again. S equals string. S equals to string. Hello from hello. String from Ahoy. Okay. To print line S okay. The value assigned to S is never read. Maybe it's overwritten before being read. Okay. So I think that is what was explained here. Okay, but what we wanted to try is what if this is not mut? So now it complains. Cannot mutate immutable variable S. So that's not possible. Because we cannot change the pointer, the capacity, the length, and the capacity S. But can we do another let? Let's see. So that is possible. So what will happen if we run this? It's still Ahoy world. There's a warning. News variable. I think this would be the next topic, which I think it has something to do with shallow copying. Is it shallow copying? No, that was shadowing. Shadowing, yeah, I remember now. So this is shadowing. But in this case, if we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. Okay, so this is clone. Let's try this out. S1, S2. Okay, so if this is S1, S2, this becomes S2, S1 dot clone. So we change this to S1 dot clone. Okay. S1 dot clone and then print this one. Correct? Yeah. This works just fine and explicitly produces the behavior shown in figure 4-3, where the heap data does get copied. Okay, so meaning if you want it to look something like this, S2 would be S1 dot clone, the clone of S1. So it's a deep copy. Okay, let's try to run this one. Yeah, S1 is hello, S2 is also hello. Good. Okay. So we just need to take note that code may be expensive. So clone itself would mean something expensive. Okay. Stack only data copy. What is this? There's another wrinkle we haven't talked about. The code using integers, part of which shown in listing 4-2 works and is valid. Yeah. So this one works. But this code seems to contradict what we just learned. We don't have to call clone. Yeah, so no need to call clone. But X is still valid and it wasn't moved into Y. Types, because types such as integers have a known size at compile time and stored entirely on the stack. So copies of the actual values are quick to make because the size is known at compile time. That means there's no reason we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying for integers. I think in data types these are scalar data types. Scalar or statically, scalar data types. Okay. Rust has a special annotation called copy that we can place on types that are stored on the stack as integers are. Okay, we'll talk more about that in chapter 10. If a type implements the copy trait, variables that used to do not move but rather are trivially copied became then still valid after assignment to another variable. If a type implements the copy trait, variables that use it do not move, but rather are trivially copied, making them still valid after assignment to another variable. Rust won't let us annotate a type with copy. Okay. You cannot put copy. If the type or any of its parts has implemented the drop trait. Okay, so that is the condition. If the type needs something special to happen when the value goes out of scope, then we add a copy annotation to that type. You'll get a compile time error. To learn about how to add the copy annotation to your type to implement a trait, okay, so we'll see that in the next chapters. Appendix C. Appendix C is where C. Derivable traits. There's so much to learn here. And we have barely scratched the surface. Okay. So what types implement a copy trait? You can check documentation for the given type to be sure, but as a general rule, any group of simple scalar values can implement copy. Okay, general rule. Any group of simple scalar values can implement copy. Nothing that requires allocation or is some form of resource can implement copy. Here are some of the types that implement copy. Integer types, okay, that one we know. Boolean, true or false, yes. Floating points, yes. Character type, yes. Okay, so up to here I think it's scalar. Tuples, if they contain types that also implement copy. For example, I32, I32. But I32 and string does not, because string is not scalar. Okay, so these things are clear. Ownership and functions. Okay, so I think this is where we partially went through the other day, and then we stopped. Okay, so let's take some time to understand this better. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a value to a function, similar to when assigning a value to a variable. Passing a variable to a function will move or copy. Okay, so automatically it will do a move or copy, just as assignment does. 4-3 has an example with some annotation showing where the variables go into and out of scope. Here's 4-3. Okay, so this is 4-3. Okay, let's inspect this one line by line. You have hello string, you bind it to s. S is not mutable. And then you have a function here. Function takes ownership. So s's value moves into the function. So that is automatic. Okay, I think it was stated here. Passing a variable to a function will move or copy, just as assignment does. Okay. After this line, s is no longer valid. So it will be free. Okay, but what's happening inside takes ownership? Okay, takes ownership. You have some string as the parameter. So some string comes into scope. And then print line, some string. Here, some string goes out of scope and drop is called. The backing memory is freed. Okay. How can we illustrate this? Okay, so what I think happened here is like, okay, so let me get my pen. So at this point, you have S, so you have the pointer, length, and capacity. Then you have hello. So pointer is pointing here. But when you got to this point, so you have some string. And C. So now this one points here. I think this part here is already yeah. But what about for scalar data type? X comes into scope, makes copy, has I32 implements a copy trait. X does not move into the function. Okay, X automatically implement the copy trait. I think that's what it was trying to say. X does not move into the function, so it doesn't move into the function. Here, some integers, Okay, some integer would be 5, while x in itself is still 5, and that's why you can still print x here. Yeah. Why don't we try it out once again? Copy this, or we can just run it from here. Hello, and 5, 5, 5, this is x. No, the first 5 is some integer. Yeah, because it goes inside and makes copy, it prints 5. And then the x here is coming from this one, 5. Yeah. Let's copy this and try it out ourselves. It here. Save. And cargo run. Let's try cargo run from here. Or I can run from here. Same thing. Okay, let's move on. If we try to use S after the call to takes ownership to here, Rust will throw a compile time error. Yep. Let's try that. Yes. Okay, so let me print 9. Ah, yeah, so it complains. Borrow of move value S. So about here. Oh, we cannot run this one because the compiler is already complaining. Do we mark it as a comment? /. Yep. Let me. Okay, so let me try to install something here in Visual Studio Code. Extension. I would like to have the VI extension so that it's easier for me to navigate. Here, install. So that will allow me to do something like this. VI src main. Okay, so these are the line numbers. Okay, I got used to this. So if I go to S, something like this. If I add a line, can do something like this. That's too far. Do a tab. Just install that in Visual Studio Code. all that. Okay. Let's go to line number 6. Let's go to the end of the line. At another line. Yeah. Okay, let's continue. Return values and scope. Returning values can also transfer ownership. 4-4 shows an example of a function that returns some value with similar annotations as those existing in 4-3. Okay, gives ownership. Where is gives ownership? Okay, gives ownership is here. Maybe let me copy this one. Student code. Can I highlight it like this? Oops. X. Swap. Paste. Space there. Expand this. Okay, so S1 gives ownership. Then we go to line 10. Gives ownership is here. Gives ownership will move its return value into the function that calls it. Okay, return value. Okay, return value is, okay, this is how you return a value from a function. Then it's string data type. Over here, we have some string from yours. So some string is in scope. And then some string is returned and moves out to the calling function. Yeah. So this is how you return values from a function. So meaning some string here will be returned by this one here, string. Okay. Gives ownership will return some string which is yours, and it's a move. So after this line, some string is no longer valid. Okay, but now you have S1. Okay, now in line number 6, S2 calls into scope. You have hello. And then in this case, takes and gives back. Yes, takes and gives back. Oh, okay, takes and gives back is here. Hello is in S2 is pointing to hello. S string will, okay, so it will be a move. A string comes into scope, and then a string is returned. Okay, so it's a move. S2 is moved to a string is returned, returned and moves out to the calling function. Okay, so it moves out to S3. Okay, so S2 moved to within the function, which is a string, and now a string moved to S3. So it means that S2 cannot use anymore, and then a string obviously we cannot use as well. Okay. Which also moves its return value to S3. Yeah, correct. Moves its return value to S3. Here, S3 goes out of scope and is dropped. S2 was moved, so nothing happens. S1 goes out of scope and it's dropped. S3 goes out of scope and is dropped. S2 was moved. S2 was moved here. So nothing happens. What does it mean? So nothing happens. S1 goes out of scope. Why nothing happened to S2? S2 is moved into takes and gives back, which also moves its return. Takes a string. Okay, so let's try to process this. S, nothing happens. Okay, we can see from the warning here also. It seems like we can still use S2. We can try. And here, S2. S2 is still here. Okay. But so S2 is type string, which does not implement the copy trait. Yeah. It's no longer valid. S2 was moved here. Why does it say S2 was moved? Yeah, that's correct. So nothing happens. Nothing happens. Nothing happened to what? S2. Let's get back to the book and see. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop. Yes. Unless ownership of the data has been moved to another variable. Unless ownership of the data has been... Okay. So, okay. So does it mean that by saying nothing happens, it means that hello is not cleaned up because we are moving the ownership from S2 to A string and then from A string to S3. So hello was not freed. And then when we print S3, of course we can display hello. Okay. Let's see. So far it's only print that this is the only statement I'm quite confident for now. Yeah. That's how it is. It's part of learning. Okay. Yeah, so hello is still there. Hello is still there. Save this. Back to this one. Okay, while this works, taking ownership and then returning ownership with every function is a bit tedious. That's correct. Because we took ownership here, and then we returned it here. And then the value is here. But what if I still want to use S2 and return something else? Let's see. What if you want to let a function use a value but not take ownership? Yeah, exactly. It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using tuple. Okay, using tuple. Let's see. S1, okay. And then we have calculate length. S1 is moved here. S1 is moved to S. Okay, so it's expecting tuple as the return where you have string and then you have unsigned integer. And then s.len, so len will return the length of a string and it is binded here to length, which is returned as usize. Okay, but what happens to s? S is returned, so S is moved. S is moved. Yeah, S1 is moved to S, and S goes out of scope and is returned to string. So this S is moved to S2. Okay. And then the length of wait. The length of S2. Okay. S2 is string. S2. So it's the length of hello is 5. That is the expected output. So, but what have we achieved here? So it means that we have returned length and then we can still use the value of hello, but it's returned here. But of course, I think S1 we cannot use anymore. Okay. So it will display the length of hello is 5. Length of hello is 5. Right. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. Okay, that's going to be the next topic. So I think we covered this the other day, but this is a review for you and me to have a clear understanding of how ownership works. Okay. References and borrowing. The issue with the tuple code in this thing 4-5 is what we have to return is that we have to return the string to the calling function so we can still use string after the call to calculate length because the string was moved. Okay, so the understanding is correct. S1 we cannot use Instead, it's moved to S2. So S2 we can print. Instead, we can provide a reference to the string value. A reference is like a pointer in that it's an address we can follow to access the data stored at that address. That data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value of a particular type for the life of that reference. For the life of that reference. Okay, so now we're using reference. Here's how you would define and use calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. So it's like we're cheating a little bit. We are cheating in the sense that, yeah, I still want to use S1, but how will I do that? So S1 is here. Oh, there's this ampersand sign. Okay. Len is returned, and we can still use S1. First, notice that all the tuple code in the variable declaration and the function return value is gone. Yeah, that's correct. Second, note that we pass ampersand S1 into calculate length, and in its definition, we take ampersand string rather than string. Yeah, so that's the difference. Ampersand, why not at sign? Okay, it's ampersand. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. Okay, so that's how you do it. So you have ampersand here, and then in the function itself, you use ampersand also. Wait, what if we don't put ampersand here? Will it complain? So let's try that. Will it complain? Mm-hmm. Function name. Let's run this one first. Okay. So now I will break this code by removing this. It will complain. Consider removing the borrow original. Okay. Arguments to this function are incorrect. Function defined here. Consider removing the borrow. Yeah. So this one, of course, we cannot use anymore. So instead, we use ampersand, and then we need to put ampersand here as well. Okay, what happened here? Reference. It's a nice diagram where we had originally S1, we had S1, yeah, this is S1, so here, you have the pointer pointing to hello, and then when you went inside calculate length, we know that S1 is a reference, so S is here, which is a reference, yeah. So you have the ampersand. Let me put the ampersand S. So this one doesn't have the len and capacity. just a pointer pointing to S1. Okay, so it means S1 will still be there. No, let's try to understand this. Okay, so that's the diagram, but we need to understand it further. Let's read through. Oh, there's another one here. Ampersand is dereferencing, which is accomplished with the dereference. Okay, the opposite of reference, okay, this is reference, ampersand, is dereferencing, which is accomplished with the operator asterisk. Okay, so the opposite of ampersand is asterisk. We use some of the difference operator in chapter 8. Okay, so let's just take note for now. Okay, let's take a look at the function call here. Ampersand S1 syntax, let us create a reference that refers to the value S1 but does not own it, because the reference does not own it. The value it points to will not be dropped when the reference stops being used. So indirectly, the reference S doesn't own hello. Okay. So hello will not be dropped. No, no, wait. Because the reference does not own it. Oh, I think I'm wrong. S1 syntax, let us create a reference that refers to the value of S1, the value of S1, but does not own it. The value of S1. By value, does it mean hello? S1 owns hello, but S doesn't own hello. Okay. The value it points to will not be dropped when the reference stops being used. Okay. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter is S is a reference. Let's add some explanatory annotations. Okay. S is a reference to string. Here S goes out of scope. Okay, the reference goes out of scope, but because S does not have ownership of what it refers to, the value is not dropped. The scope in which variable S is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when S stops being used, because S doesn't have ownership. Okay, so this S is a reference. It doesn't have ownership. When the function references as parameters instead of actual values, you don't need to return the values in order to give back ownership, because we never had ownership. Okay. Okay, to return, okay, because now it looks like this. Without the ampersand, S is moved into here, into the parameter. And if we want to retain or display hello, we need to return hello over here to another variable, string variable, and then we can display it. But in this case, if we just use the reference, it's just pointing to S1, yeah, we can still return the length of the string, but S1 here will not be freed. So we can still print S1. Because in this case, S doesn't own it, and it will not be freed. Okay. We call the action of creating a reference borrowing. So this approach is borrowing. So ampersand will translate to S1. I'll borrow S1 at the time being because I need to process it here and return something, which is moved to len. No, it's not moved. It's copied because this is scalar. Okay. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. Yeah. So from now on, if I read the function, calculate length, I'm borrowing S1 from you temporarily because I need to use it somewhere here and give it back to you with interest, something like that. Okay, so what happens if we try to modify something we're borrowing? Modify something we're borrowing. Okay, does it mean that I want to change the value of S1, not just hello? Maybe I'll put hello. Try the code in listing 4-6. Spider alert doesn't work. Okay, okay. Let's see. Change is the function. So let's try to interpret this. Okay, hello is binded to S. S is not mutable. And I'm borrowing the value of S here. Then inside change, yeah, it becomes some string, but it's referencing S. Some string is referencing S. Some string doesn't directly own hello. And then some string, okay, so this is assuming you have hello world. But why it doesn't work? It doesn't work because S is not mutable. So you cannot change the value of S. Or there's another reason. Okay, let's see. Cannot borrow some string as mutable as it is behind a reference. Okay, so in the first place, it's not mutable. And it's behind a reference. So some string cannot directly change the value of hello into hello world. Consider changing this to be a mutable reference. Oh, okay. Some string at mute or mut, at mut. I'll call this mute from now on. At mute, mutable string. Okay, let's see. We can fix a code to allow us to modify a borrowed value with just a few small tweaks that use instead of a mutable reference. Okay. So it's like I'm referencing a variable, but in order for me to change it, I need to say it's mutable. So it should be defined as mutable here, and then mute, borrow. Then I can change some string push str. Hello, this one becomes hello world. So here, if we display S, it should be hello world. Okay, this is interesting. Let's try this one. Okay, that has changed. So means if I do a print line here, this should be possible, and then should print out hello world. Errors, yes, correct. It's hello world. What will happen if I will return something with interest? You 32. I'll put you 32. So unsigned 32. Then here, let me put that L equals this one. Then here, let's return some string dot length. I should remove semicolon because it's return value. Okay. Oh, no, this one mismatch. Expected U32 found U size. Oh, I think len returns U size. Can convert U size to U2 and that's not it. How do we convert? Convert here. No, not convert. How do we convert it? U32? No. Okay. Let's figure it out later. Size. No. And here is U size. U size, then I see no error. String U size is already U size. By default, that is U32. Okay, so we need to force it to U30 U size. Okay, so let's run this. Hello world. Is equal to then is equal to 12. Okay, because now hello, it's now hello world. Okay, so that is clear. Okay, let's move on. Substring. Okay, mutable references have one big restriction. If you have a mutable reference to a value, you can have no other reference. You can have no other reference to that value. This code that attempts to create two mutable references to S will fail. Okay, mutable at mute S. So R1 is a reference to a mutable S. And R2 is a reference to a mutable S again. Okay, so there's an error. Cannot borrow S as mutable more than once at a time. So it's a strict rule. Okay, so we cannot do that. But before making that mistake, of course, the compiler will inform us. Yeah. This error says that the code is invalid because you cannot borrow S as a mutable more than once at a time. The first mutable borrow is R1. And must last until it's used in the print line. But between the creation of that mutable reference and its usage, we tried to create another mutable reference, R2, that borrows the same data as R1. Yeah. Okay. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new rustaceans struggle with because most languages let you mutate whenever you'd like. Rust means that you cannot do this. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition that happens when this tree behavior occurs. Okay, so data race, similar to a race condition, and this tree behavior occurs. Two or more pointers accessing the same data at the same time. At least one of the pointer is being used to write to the data. There's no mechanism being used to synchronize access to the data. Okay. So if at some point R2 changes S, so R1 should see S as well, S as hello. Yeah, but what does it mean here? Two or more pointers access the same data at the same time. Okay. Okay, one pointer is being used to write to the data. So one pointer is writing data. Maybe it's hello, and then it tries to change it to hello world. There's no mechanism being used to synchronize access to the data. There's no mechanism being used to synchronize access to the data. Oh, it means that you have a data race if, okay, this tree occurs. Okay, understand. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. It's a strict rule, so we're learning Rust, so we'll just accept this. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Okay, so you can make use of curly brackets to create a new scope, yes. Curly brackets within function that is totally acceptable. Allowing for multiple mutable references, just not simultaneous ones. Okay, so let's see. S is mutable, can be changed. Within this scope, you have R1 referencing a mutable S. R1 goes out of scope, so we can make a new reference with no problems. Okay. Because R1 is out of scope here. So it means that you can have another R2 here referencing S. Yeah. Rust enforces a similar rule for combining mutable and immutable references. This code results in error. Okay. There's a little bit of difference here. Why do we have no problem? Okay, because S, what? This one is mutable. This one is not mutable. So it's allowed. We're just referencing S, but probably we're not planning to change the value of S at this point in time for this reference. Same for this one. But this one, R3 has the intention to change the value of S, and R3 is referencing S. These two are referencing S also. Okay, so what's the reason? Let's see. Okay, no problem. Immutable borrow occurs here, so this is allowed because we're not planning to change S. Okay, same for this one. Mutable borrow occurs here. Okay, big problem. Mutable borrow occurs here because we're planning to change it. Mutable borrow later used here. Here, we also cannot have mutable reference while we have an immutable one to the same value. Oh, so it means that if you mix mutable and immutable, even though you're referencing, but you're pointing to the same value, that is not allowed. Okay. Users of an immutable reference don't expect the value to suddenly change out from under them. Yeah. I mean, it was immutable in the first place. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. Okay. Multiple immutable references are allowed. Okay. So at this point, when the compiler sees this, okay, you have S, it's immutable. Now somebody is referencing S as well, so that is fine. Because nobody can change this. But once you make it mutable, then that's a big problem. Note that a reference scope starts from where it is introduced and continues through the last time the reference is used. For instance, this code will compile because the last usage of the immutable references is in the print line before the mutable reference is introduced. Okay, so R1 and R2 is totally fine. R1 and R2 doesn't have any plans changing hello. Variables R1 and R2 will be used after this point. So R1 and R2 are not used. However, here R3 also no problem, and you can display print lines. Oh, so hmm. Okay. At this point, I'm not planning to change it anyway, but here it's being changed. Why it's allowed now? A references scope starts from where it was introduced and continues through the last time that reference is used. Ah, okay. Because of the print line statement, and now we're using a reference. After this line, it becomes out of scope. Okay. So using it means it becomes out of scope also. Scopes of the immutable references R1 and R2 end after the print line. Okay. Where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so this code is allowed. The compiler can tell that the reference is no longer being used at the point before the end of the scope. Even though borrowing errors may be frustrating at times, remember that it's a Rust compiler pointing out potential bug early at compile time rather than at runtime, showing you exactly where the problem is. Then you don't have to track down your data isn't what you thought it was. Okay. Okay. Oh. So just in case we get confused, Rust compiler will point out all these details, we fix it, and we won't have any problem in the future. Okay. What about dangling references? In languages with pointers, it's easy to erroneously create a dangling pointer that references a location in memory that may have been given to someone else, by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be. Okay, so there's that guarantee. Compiler guarantees references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. Okay, so let's try to create a dangling reference to see how Rust prevents them with compile time error. Okay, so let's try to analyze. You have a function dangle. Okay, the return will bind it to reference to nothing. Dangle doesn't take in any parameters. It returns a reference to a string. So we have string here, S. Within the scope, we have S, which is immutable. We're not planning to change low, so ampersand S is totally fine. And then we pass it here. Okay. And then I'm wrong. Here's the error. Expected named lifetime parameter. This function's return type contains a borrowed value, but there's no value for it to be borrowed from. Consider using static lifetime, but this is uncommon unless you are turning a borrowed value from a const or static string. Okay. If you want to make it static, you have ampersand static string. Okay, so from ampersand string to string. returns a reference to a data owned by the current function. Okay, so why it's dangling? Dangling, okay, so you have a reference, returns something. Okay, is it because S is no S is pointing to something that is out of scope. So outside dangle, hello is already free. But this one is still pointing to that location. Yeah, okay. This error message refers to a feature we haven't covered yet. Lifetimes. There's another feature. Lifetimes. We'll discuss lifetimes in detail in chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. Okay, let's see. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Let's take a closer look at exactly what's happening at each stage of our dangle code. Okay, dangle returns a reference to string. Okay, correct. S is a new string. We return a reference to string S. Here, S goes out of scope and is dropped. S goes out of scope. Yeah, correct. Hello is freed up. So its memory goes away. Danger. But dangle, what does dangle have now? It's just a reference to some empty space, probably. Because S is created inside dangle, when the code of dangle is finished, S will be deallocated. Yeah, so it will be freed. But we try to return a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return the string directly. Return the string directly. Yeah. Where's the original code? Return the string directly. So you just move the value to reference to nothing. Of course, yes. This will work. This works without any problems. Ownership is moved out and nothing is deallocated. Okay. The rules of references. Let's recap what we have discussed about references. At any given time, you can have either one mutable reference or any number of mutable references. Wait. One mutable reference, that's correct. You can have number of immutable references, that's correct. But it has to be out of scope. I think if I remember correctly, this part here. So this is allowed because R1 and R2 will not be used after this point. Yeah. Yeah, I think the statement to explain this part should be here. Or any number of immutable references. Either one. Oh, wait. I think I'm wrong. Either one mutable reference. Okay, you have one mutable reference. Or any number of immutable reference. Yeah, so this is correct. This is correct. This is correct. That one explains that part. The references must always be valid. Okay, so that explains this part. So after this part, you cannot use R1 and R2 anymore. Next, we'll look at different kinds of references, slices. Okay, let's try to finish this one and call it a day. Then maybe, oh, this one is also quite long. The slice type. Slice type. I think this is going to take another hour, it seems, but let's try. Okay, the slice type. Slices let you reference a continuous sequence of elements in a collection rather than the whole collection. A slice kind of reference, so it does not have ownership. So you're slicing elements in a collection. Okay. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word. So the entire string should be returned. Okay, so we're slicing the string. Let's work through how we'd write the string signature of this function without using slices. To understand the problem that slices will solve, why do we have a question mark? Maybe let's prepare another project for this ownership. So cargo new slice. First word function has a reference to string s as a parameter. We don't need ownership, so this is fine. Okay. In idiomatic Rust, functions do not take ownership of their arguments unless they need to. And the reason for that will become clear as we keep going. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word indicated by a space. So let's try that as shown in 4-7. Okay, size, it will return size, bytes, so s as bytes. Okay, let's just assume that it is represented as bytes and it's stored here. Then we have a for loop. Okay, so I and a reference to an item in bytes. Okay, bytes. And as an iterator, we enumerate. Okay, so it's like going through the contents of this. And we are returning, what are we returning? Return I, okay. If this one looks a bit strange. So we can use item here inside. Yeah, of course. Yeah, item, a reference to an item, equals to B. This is B. B as byte. Yeah, B as byte, space. Yeah, there's a space. It's clear. There's a character inside. Byte, character, space. If item, so we're going through byte per byte. Item finds a space, and within this scope, you return I. What is I? What is I? S dot length. I don't know what is I. Okay. Because we need to go through a string element by element and check whether a value is a space, we'll convert our string to an array of bytes using as bytes. Okay. Now, next we create an iterator over the array of bytes using ITER, so that's iterator. We'll discuss more in detail. Okay, what's in chapter 13? Function, iterators. Okay. ITER is a method returns each element in a collection that are enumerate. Wraps the result of iterator and returns each element as part of a tuple. Okay, so it will return as part of a tuple. The first element of the tuple returned from enumerate is the so I is an index. I is an index. Okay. And the second element is a reference to the element. It's a bit more convenient than calculating the index ourselves. Oh, it's quite convenient. Okay. Because enumerate method returns a tuple, we can use patterns to destructure that tuple. We'll be discussing patterns more in chapter 6. Okay. Irby. Maybe that's after another week. We'll see. In the for loop, we specify a pattern that has I for the index in the tuple and single byte in the tuple. Because we get a reference to the element, we use ampersand in the pattern. Reference to the element item. Okay. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using slength. Okay, if we find a space, this is the space, we return the position, so that's the index. So it is returned via this tuple. No, yeah, returned via this tuple. Okay. Now we have a way to find out the index of the end of the first word in the string because there's a problem. We're returning use size on its own, but it's only a meaningful number in the context of ampersand string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in listing for the shape. It uses the first word function. Slen. Okay. Return, because this is a function, return once it encounters a space, then immediately the function will return. So use size is actually the index, not the slen. Yeah. If it's just one word, there's no space, then it will return the length. Okay. Yeah, U size. Yeah, because of this. Okay, so how about this one? Hello world, first word. Where's the first word? Oh, maybe it's referring to this one, first word. Okay. Word will get the value 5. Word will get the value 5 from hello world because it will return the index 0, 1, 2, 3, 4, and then space. It will return index 5. Yeah. Value 5 is from index 5. Okay. S dot clear. This empties the string, making it equal to empty. S clear. S clear, yeah, because it's mutable string, so we can change the value of S. And over here, we are borrowing S. Borrowing S because of the percent. The value 5 here, but S no longer has any content. Could meaningfully use with the value of 5, so word is now totally valid. This program compiles without any errors and would also do so if you use word after calling sclear. Yeah. Okay, let's check first word again. We're just borrowing S. How about here? It's from bytes. Oh, slen was not used because we're doing I from here. Because word isn't connected to the state of S. Okay, word is not connected to the state of S at all. Word still contains value 5. You could use the value 5 with the variable S to try to extract the first word out, but this would be a bug because the contents of S have changed since we saved 5 in word. Content of S have changed since we saved 5 in word. We could use that value 5 with the variable S to try to extract the first word out. But this would be a bug because the contents of S have changed since we saved 5 in Word. Word isn't connected to the state of S at all. Okay. Word still contains the value 5. Yeah. Okay. Because of this, it's moved into Word. Look, there's some diagram here. That is different topic. And okay. Having to worry about the index in Word getting out of sync with the data in S is tedious and error prone. Managing these indices is even more brittle. If you write a second word function, its signature would have to look like this. Second word. Use size. Now we're tracking a starting and an ending index. And we have even more values that were calculated for the Okay, well, three unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution to this problem. String slices. A string slice is a reference to part of a string, and it looks like this. Okay, so we have hello world, hello. Okay, so we have a reference to S, 0 to 5, so that's 0 to 5. And world, reference to S, 6 to 11. Okay. So it's like two references pointing to the same thing. At this point, okay, how to interpret this? They have no plans changing the value, so it should be valid. Rather than a reference to the entire string, hello is referencing a portion of the string. Okay, so it's like there's a range here from 0 to 5. Starting index, ending index. Starting index is the first position in the slice, and ending index is on more than the last position in the slice. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus starting index. So in the case that world equals to 6 to 11, world would be a slice that contains a pointer to the byte at index 6 of S with a length value 5. Okay. So it looks like this. S points here, length is 11. S points to hello world. Okay, but world, yeah, this is S, this is not hello. So world, however, points to 6 and length 5 with length value of 5. So that is calculated from ending index minus starting index, length of 5. Because world is a string. World is a string. It needs pointer length and it should have capacity. How come this one doesn't have capacity? Capacity would be 1, 2, 3, 4, 5. Okay. With Rust's dot range syntax, oh, I didn't know that. I just assumed that that's a range 0 to 5. Okay. If you want to start at index 0, you can drop the value before the two periods. Drop the value before the two periods, meaning this side. Okay. Yeah, like this. Okay. So the length of slice 0 to 2 is equal to slice s dot 2. Slen len. So the length of hello 5. So they are equal. Yeah, these are equal. Output. You can also drop both values to take a slice of the entire string. Okay, so you can do dot. Where can we use this? You can just point it to S. String slice range indicates as a core. Indices must occur at validity of character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. The purpose of introducing string slices, we're assuming ASCII only in this section. More through discussion. Yeah, UTF-8 encoded text with string. Okay, so if it's UTF-8, it's not ASCII. Okay. With all this information in mind, let's rewrite first word to return a slice that types the significant string slice is written as at str. Okay, first word, borrow, referencing s, so it's a borrow, returns a reference str, convert it as bytes, for loop, bytes, iterator, enumerate, creates a tuple where you have the index and a reference to the item. If it's a space, returns a reference to 0 to I. So if we have hello world, then that's just hello. Okay, so if we only have hello, for example, hello, so there's no space, then it will return a reference to because ampersand is here, a reference to hello, for example. We get the index for the end of the word the same way we did in this thing 4-7 by looking for the first occurrence of a space. Find the space, we return a string slice using the start of the string and the index of the space as the starting and ending slices. Now when we call first word, we get back a single value that is tied to the underlying data. The value is made up of reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for a second word. Okay. Now we have a straightforward API that's much harder to mess up because the compiler ensures reference to string remain valid. Remember the bug in the program in listing 4-8? When we got the index to the end, of the first word, but then cleared the string, so our index was invalid, clear, immutable. Code logically incorrect, but didn't show any immediate errors. First word is word, so word, okay, S, hello is inside the word, and S is cleared. Okay, let's see the explanation. Immutable borrow occurs here. Okay, immutable borrow occurs here. First word is word, immutable borrow later used here. Okay, call from the borrowing rules that if we have an immutable reference to something, immutable reference to something, but this is mutable, we cannot also take a mutable reference because clear needs to truncate the string. It needs to get a mutable reference. Okay, print line after the call to clear uses the reference in word, so the immutable reference must still be active at that point. Rust disallows the mutable reference in the clear and the immutable reference in word existing at the same time. Mutable reference in clear, because it's S, it's mutable, while word is immutable from existing at the same time and compilation fails. Not only has Rust made our API easier to use, but it has also eliminated the entire class of errors at compile time. So what's the solution? Do we fix this? This is mutable, then word should be mutable. Let's see. String literals as slices. Recall that we talked about string literals being stored inside the binary, but now we know about slices, we can properly understand string literals. Okay, so this is string literal. The type S here is a reference str. It's a slice pointing to the specific point in the binary. This is also why string literals are immutable. At str is an immutable reference. String slices as parameters. Knowing you can take slices of literals and string values leads us to one more improvement on first word, and that's its signature. Okay, first word, person, reference, S, reference str. Experience station would write the signature shown in 4-9. Instead, because it allows us to use the same function on both string values and, okay, so string and literals. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of the reference, deref, I think that's the reference, or deref coercions. A feature we'll cover implicit deref coercions and functions and methods, chapter 15. Defining a function to take a string slice instead of a reference of a string makes our API more general and useful without losing any functionality, okay? Function to take a string slice instead of a reference to a string. How is that done? Hello world, my string, word, first word. First word. So they did not change the first word function, but only this part. Okay. First word at my string, 0 to 6. My string, borrowing. This is immutable. Borrowing 0 to 6. 0, 1, 2, 3, 4, 5, 6. So it's until here. Word, first word, my string, everything. First word also works on references to string, which are equivalent to whole slices of string S. Let word equals first word. Yeah, it is fine. My string literal hello world. Okay, so it's not my string anymore, but my string literal. First word works as a string literals, whether partial or whole. Okay, so this is fine. 0 to 6. 0 to 6. So you can still use this one because it was changed to string literal. It's now string. Yeah, so you can do the same thing. The string literals are string slices already. This works too without the slice syntax. Yeah, so you can work like this. Okay. Other slices. Oh, we're almost done. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. Consider this array. Okay, just as we might want to refer to part of a string, we might want to refer to part of an array. Same. We have the range. This slice has type I32. It works the same way as string slices do, by storing a reference to the first element and then. We use this kind of slice for all sorts of other collections. We'll discuss these collections in detail. Okay, what I will do, maybe, let's see. Okay, so this is for slices. Let's copy first word. And let's copy this one. So we have to change this and make it str. Okay, so let's skip that. Let's run, let's see. Nope, we're not printing anything. Let's come back here. Okay, so we can do array slices also. Let's put it here in our code for reference. Okay. So this. Two, three will be the output. Total of 5 of I32. Reference slice is referencing A from 1 to 3. 1, 2, 3. So, and then slice some 2, 0, 1, 2. Three. It's the output. Not equal. Not equal to true. Tap into assert. Did I save it? Macro will print the values of the expression with their debug representations. string middle, slice. What do we see this as? On panic. Mm, maybe we'll research more on assert later. Okay. Okay, summary. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compiled time. The Rust language gives you control over your memory usage in the same way as other systems programming languages. But having the owner of data automatically clean up that data the owner goes out of scope means you don't have to write and debug extra code to get this control. Excellent. Ownership affects how lots of other parts of Rust work. So we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping pieces of data together in struct. So that's it for now. We end here and let's continue in another video, hopefully in the next day. But of course, we'll go through once again some parts just to review and so that we won't forget the important concepts before we move on. All right, so thank you for watching. Have a nice day. Bye for now.